Assalamu alaikum. This is the chapter 17 of machine design by Shigley. The topic of today's lecture is flexible mechanical elements. All of you almost always seen the flexible transmission elements like belts, rope, chain, and other similar flexible elements. There are flexible shafts as well. The basic purpose of these elements to transmit power from one shaft to another shaft, which are separated by long distances. Because from one shaft to another shaft, usually we transmit power through the help of gears. But when the shaft distance are very large, we need to have very large gears, or we need to have uh, a set of small gears, which will cost a lot uh, because the gears are made of metals, and due to heavy metals the inertia of the system will be high. That's why for longer distances we prefer belts, rope, chain, and other types of flexible elements. These elements can be used to replacement of gears, that is for sure. These Their use simplifies the design of machine and substantially reduce the cost, as the gears for long distance using gear will cost uh, increase the cost, and also a lot of maintenance will be required. As compared to them, belts are very cheap and cost effective elements. As these elements are elastic and long, that's why they absorb shock, and they provide a damping in the shafts, and therefore the vibration will not be transmitted through the from one shaft to another shaft. Most of the elements do not have infinite life. That's why we have to establish inspection criteria to check these elements regularly. And whenever the first impression of failure arises, we have to replace these elements. Most common elements are belts. There are four basic type of belt. We have flat belt, round belt, V belt, and timing belt. Almost all of you have seen the V belts, like in water pump motor. We have V belts, and in cars as well. We have a lot of V belts. Timing belt is the belt we use when precise motion of driver pulley and driven pulley is required, like in case of camshaft. In case of cars, we required a precise motion of camshaft with reference to crankshaft. Vice versa. In other words, we have to precisely monitor the motion of piston and valves. That's why we have to have precise motion of camshaft, which is attached to valve, and crankshaft, which is attached to piston of the car. That's why we have to use either timing belt or in some cases chains. In case of flat belt, we have to use crown pulleys. This is the example of crown pulley. Because of centrifugal force, the pulley is pushed further away from the center, and due to that motion, the pulley comes at the center of the belt comes at the center of the crown, and it will not be removed from the pulley while rotation. In case of V belts and round belts, we make grooves in the pulley, these type of grooves, and V belt is inserted within the grooves. And timing belts, in case of timing belts, we have toothed wheel and or sprocket, and similarly in the belt we also have teeth, and these teeth are attached or fixed in the slots of the pulleys or sprocket, and due to that we have a precise motion of pulley with respect to belt, or belt with respect to pulley. In all cases, the pulley axis must be separated by a certain minimum distance. Minimum distance has a limit. That's why these are given here. So in case of V belt and timing belt, we have a limit of central distance. These are limit of upper central distance, and in case of flat belt and round belt, we don't have upper limit of uh, central distance of the two pulleys. Belts are used for longer center distance, except for timing belt. This is in timing belt, because we have grooves on the belts, teeth on the belt, and groove in the pulley. that's why there is no slippage. Otherwise, in all the other belts there is some slippage, and due to that slippage, the ratio of uh, N1 by N2 RPM ratio and D2 by D1 diameter ratio is not fixed. How we calculate this? We know that RPM is equal one revolution circumference, or say circumference is equal to 2 pi r, or equal to pi d. For one revolution we will be covering a circumferential distance of 1, so n1 will be equal to pi d1. Similarly, n2 will be equal to pi d2. If we have a diameter ratio of 1, n1 will be equal to n2. If diameter of d1 is 2 times d2, then n2 will be 2 times n1. So that is the equation we get in when there is no slippage. But as in case of flat belt and V belt, there is some slippage, and due to that slippage, the ratio will not be fixed. Either ratio is more or less than the diameter ratios. That's why it is not fixed. But for the sake of calculation, we have to assume these calculation equal. The angular velocity ratio between the driving and driven shaft is neither constant nor exactly equal to the ratio of the pulley diameter. So the slippage will either increase or decrease with the time. In some cases, an idler or tension pulley can be used to avoid adjustment at central distance, as we have to make a proper tension within the pulley, and with the time pulley flexibility of pulley increases, and we have to tighten the belts again. Due to that, we have to move the pulleys away from each other, or we can add some idler. What is an idler? If this is a pulley and this is a second pulley, we have belt. If with the time, let's say the initial tension is decreased, we can add a tensioner here. If we push the tensioner inside, it is an idler which is only rotating with the help of belt. When belt is moving, it will rotate. If we apply this, the belt will be there will be initial tension in the belt, so that this tension. So due to this tension, belt will be tightened. So the throughout the life of the belt, the tension can be adjusted through the help of idler or tensioner. So these are the examples: idler pulley or tensioner pulley. This one and this one. There we have two type of driving mechanism. One is open belt drive, and second is cross belt drive. In open, what is the difference? In open belt drive, you say that if the driver shaft is rotating clockwise, so as the driven shaft is also rotating clockwise. But in case of cross belt drive, we invert the direction of motion. Here the driver shaft is rotating clockwise, and driven shaft is rotating anti-clockwise. In case of belt, we have two types of drive. Like this is the driver shaft. This is the input power. It's applied to this pulley, and this pulley is pulling the belt towards it. That's due to this pull that this side will be tighter side, and after rotation, this pulley is pushing the belt towards already existing belt. So there will be less tension on this side, or this side is called a slack side. This is tight side, and the other side will be called slack side. Most of the time you use top surface as loose side, because if it is loose side, the contact area will be increased. If it is on the bottom side, loose side, the contact area will be decreased. And in case of belt drive, we required higher amount of friction between belt and pulley. In other words, we required zero or no slippage. Due to that, to decrease the slippage and increase the power transmission, we have to have larger contact area. So more the angle of contact, more will be the friction, and more power will be transmitted. So this is a very important parameter, the area. We have just said the cross belt drive has a one purpose of rotation of inverting the direction of rotation. The direction of rotation can also be inverted by adding two idlers. These two idlers are added. We have throughout the loop we have open belt drive, but the direction of rotation has been inverted. But in this case, we have to keep in mind that here this side is in contact with the pulley, and going towards other side, this side is out. The side which was in contact with Left pulley is now outward side, so inward side will also be frictional side. So in this case we have to have both sides with friction material added to it, because both of the surface of belt are in contact with the pulley in this specific case. Advantages of flat belt over other belt. One of the advantage of flat belt is that we can transmit power between the shaft which are not parallel to each other. Here we are seeing that the two shafts are right at 90 degree to each other, but the power can be transmitted. The only point to keep in mind is that the midpoint of driver shaft, driver pulley, and the midpoint of driven pulley must be in line of each other. Uh, Also, there must be some idler or guide pulleys must be provided to transmit to move the belt from this pulley to that pulley. So that must be provided. So that is one of the advantage of flat belt. Second advantage is that it can be used as a clutch. What is clutch? If driver pulley is rotating and a power is transmitted to a belt, the driven pulley will be rotated as far as the driver pulley or input power is there, in or out. But what is the purpose of clutch? We can disengage output power from input power. So if we apply this fork, if we move this belt from this fork to this direction, there is a loose pulley which is not attached to anything. So the belt will move to this pulley and input power will be there, but it will not be transmitted to output shaft. So that is a purpose of clutch, which we can obtain easily from a flat belt. Also we can apply we can have a variable speed, like let's say this is an input and this is output shaft. Only by changing the pulley towards left and right we can change speed ratios, because input rpm is same, and by changing pulley to this direction for smaller rpm we can change output rpm, we can increase output rpm, or by moving towards right for same input rpm we can decrease output rpm. So these ratio can be changed by just adjusting the pulley towards right and left, and this is continuous variable. And the second one is step variable. Step variable is that we have fixed diameter of pulleys of input shaft and output shaft. We can just change the belt from one pulley to another pulley on left or on driver or driven shaft, and by moving this we can achieve different motion, like in the small cycles, bicycles, you have uh, different type of sprocket on the front pedal side and on the wheel side, and by changing the sprockets you can either change the torque, speed, whatever you can manage. Same case goes for the cars. First gear is we provide a better torque in first gear, but for higher speed you have to go on the fourth or fifth gear. So that is the basic purpose of clutches and variable speeds. Flat belt material, we have different type of materials. Usually outer material is made of urethane or rubber, because it has to provide friction when comes in contact with the pulley. The friction has to be more, but also there is some tension because the pulleys pull the belt towards it, and also the belt has to transmit power. That's why there is a lot of axial load, and to resist that load we have some metallic rods, steel wires within the pulley. One of the other advantages of using flat belt is that it does not come in standard size. Usually we have a roll of flat belt. We calculate the length required for the specific purpose, and then we cut the belt. And for example, if we cut this is a belt, we cut two ends of the belt, and after that we join this end with this end to get a circular belt, and this is a machine used to join these two ends. Also, to transmit power, instead of using one wide belt, it's better to use multiple small width belts. In case of V belt, the material, instead of using wires we use nylon or nylon fabric or rayon fabric. In contrast with flat belt, V belts are used with similar sheave and shorter center distance. The center distance in case of V belts are center distance are smaller. Also, efficiency is less. In case of flat belt, we have 98% efficiency, but in case of V belt, we have 70 to 96% efficiency. Also, they come in standard lengths. So if you go in market, you will see these type of numbers in V belts, and these numbers shows which material they are made from, and what is their shape, cross section shape, and what is the length. So if you're required to change any belt in, let's say in your car, the mechanic will tell you the number, and you have to buy belt according to that number. So in market, you have a lot of shops which are only dedicated to belts. Also, we have timing belt. This is the example of timing belt. This is camshaft. We have valves attached to here, and this is crankshaft. We have a connecting rod, and on top of connecting rod we have a piston. The motion of piston and motion of cams, input valve and output valve, are precisely controlled. That's why we have to have precise motion of this left cam shaft, right cam shaft, and this connecting rod. So in because the motion is precise, we have to use a precise material for motion. We can either use a timing belt or chain. Like in my car, I have seen that they have used chain in my car. So you can see in your car either it is chain or timing belt. Timing belt has to be precisely checked, because whenever you are going on a long route and by any means if timing belt fails, the whole car will be jammed. You cannot push the car, you cannot move the car from its position, you have to tow it. So that's why the because our whole power transmission of the car is within this chamber. Whole input power is coming from that. And if you can assume how much rpm is there in normal driving, this system is moving at 1000 to 2000 revolution per minute. And let's say if this belt fails, input power is coming but valves are not opening because this belt has been failed. If valves does not open, all of the heat is in the engine, in the chamber, in the piston cylinder chamber, and that can damage whole engine of the car. So a simple belt, I think a normal belt, timing belt, cost around 1000 rupees. Expensive one cost around 1000 rupees, and for simple Suzuki and Mehran you can buy it at 4 to 500 rupees easily. So one small belt can cost you whole engine of the car. So that's why this timing belt is very important function. Because there are tooth on the belt and also grooves on the pulley, there is no extra friction needed. We have to only uh, mount the belt on input and output pulley, and the motion will be the power will be transmitted. Disadvantage of disadvantage that its cost is slightly higher than V belt and flat belt. Now coming towards mathematical calculation of the belt. For flat and V belt and open drive, we need to have how to calculate the total length of belt required for a specific assembly. A flat belt drive has efficiency of 98%, I have told you, and V belt drive has efficiency of 70 to 96%. So belt has higher efficiency. Also, flat belt produce little noise and absorb most of the belt vibration. So we have usually it's better to use flat belt. For open belt drive, the contact angles are required to be found. So while going towards calculation, the first thing comes in mind is the contact angle. Contact angle as the function of the smaller diameter of pulley and larger diameter of pulley. So just going towards uh, the mathematical model, let's say we have two pulleys, one of smaller diameter, one of larger diameter. These two pulleys, we have a belt wrapped around these two pulleys. We have the central distance of two pulleys equal to c. Also, what is known, we have diameters known. we need to calculate this length from this length. How to calculate this length? Let's make a parallel line parallel to this another line, which is this one. And what does this line shows? This line is also equal to this. Let's say this value is x, so this will also be x. This is c, this is x, and what is this length? This is capital R minus small r, radius of larger pulley minus radius of smaller pulley, as this is equal to r. So we get a right angle triangle with base length equal to x, the hypotenuse equal to c, and this equal to r minus r or d minus d by 2. So using Pythagoras theorem, x square is equal to c square minus d by 2 whole square. So we have x square is equal to c square minus d by 2 whole square. And what we get from here, x square, we need to calculate x square is equal to, it gives us 4. So 4x square equal to 4c square minus d whole square. And x is equal to, what is x? X is equal to square root of this and 1 by 2. This 4 comes here, 1 by 2. Initially square root will give us 2, and then this 2 comes here. So we have 4c square minus d whole square. This is the length we can calculate from here. So we have this length. From this length we can calculate overall length of belt for this drive, but also we need to calculate this angle. And what is this angle? This angle, let's say this angle is equal to theta. So this is also theta, and this angle is also theta. And how to calculate this theta? This theta, sine theta, is equal to what was this? R minus r or d minus d by 2. D minus d by 2 divided by this length, which was equal to c, d minus d by c. So or theta equal to sine inverse of d minus d by 2c. So this theta is equal to d minus sine inverse of d minus d by 2c, and this is also sine inverse of d minus d by 2c. So as this is smaller pulley, the angle will be less than 90 degree. For larger pulley, angle will be more than 90 degrees. So for the smaller pulley, this 180 sorry 90, not 90, more than 180 degree. So 180 minus this angle, and for larger pulley we have an angle of contact equal to pi plus this angle. So we can calculate this value. Similarly, for cross belt we can also calculate the value. The only difference is that for cross belt, both the thetas for larger pulley and smaller pulley, theta will be same. And you can see directly from the equation that in case of flat belt, sorry, in case of cross belt, the contact angle is larger. It means that friction will be higher and there will be less chances of slippage in case of cross belt. Also, how to calculate total length? We had this equation. For this equation, half of 4c square minus d plus same length will be here. So this plus this value will be 4c square minus d whole square. This term will be sum of both, plus this distance. What is this distance? We have d, this length is equal to d theta d, s is equal to r theta, or this length is equal to d theta d. Sorry, not d by 2, sorry, r theta. So final distance will be equal to this term, which is half of this plus half of this, which will give you this term, plus half of d theta d plus d theta d. So this will be a total belt required, and this can be calculated if you know the central distance between the two pulleys and diameter of both the pulleys. You can calculate the length of belt required for that specific assembly. So that was the first initial part of the calculation. Now going towards the actual calculation of flat belt drive. First of all, we need to know how flat belt drive works. Let's say we have two pulleys, a belt is attached, and this is driver pulley and this will be the driven pulley. Driver pulley means it is input shaft and this is output shaft. At this point, when this pulley is rotating, it will pull the belt towards it. It will pull the belt here. At this point, the initial so the belt will start moving with the same velocity as pulley, and there will be tension in the belt. After this point, the velocity of pulley and belt will be constant up throughout the motion up till they reach at this point. At this point, the belt will leave the pulley towards already existing belt. So there will be the pull from the pulley, pull in the belt, and there will be the push in the belt. That's why due to that push, this side will be slack side and that will be a tight side, because there is already initial tension present and this pulley is pulling, so the tension will in this pulley will be increased, and there is already initial tension in upper side, but there is a push to push off towards the belt, so that tension will be decreased. So that is the basic phenomena of belt drive, and due to this pull here and this push here, this pull push pull motion causes a phenomena which is called static creep, elastic creep. This is called elastic creep, and this elastic creep causes failure in the belt. Usually in case of belt, we have higher coefficient of friction, and you can also see this in the table, I think 17-2. They have given coefficient of friction for different types of belts. Now coming towards mathematical calculation, the mathematical calculation has two parts. First part covers, for example, coming to this figure again, first part covers the mathematical model when the belt comes in contact and when the belt leaves the contact. So in this area, what is the change in force of tension in the belt as a function of contact length? This is contact angle, contact length, or contact angle. So F force is calculated as a function of theta. Let's say theta. So that is the first, that will be the first part of the calculation. In the second part, whenever we make our belt assembly, what we do, we provide an initial tension either by for that we can just move this whole wheel to whole pulley towards right, and due to that there will be some initial tension. The second part will deal with the tension in the belt for this portion. Initial part will be the smaller portion, and the second part will be for the larger portion. This smaller portion will give us forces in the belt top and bottom surface of belt as a function of theta. This larger portion will give us the same forces F1 and F2 in terms of pretension and coefficient of friction. This will also give not coefficient of friction, centrifugal force. So at the end we will get our values in terms of pretension, theta, and centrifugal force. So we will solve mathematically in two parts. The first part, for this pulley, let's say this is the pulley, and we know that this is the total area of contact, or angle of contact. For this angle of contact, we take a smaller section and we cut this smaller section in like this, or like a slice of pizza. And for this smaller section, what are the forces here? This whole angle of contact is called theta. In that theta, we took a small angle of contact of angle d theta. For that, we have assumed that the belt is moving is in this direction, pulley is rotating in this direction. Due to that, there is a frictional force in this direction. Because the belt is already, because we tied the belt, due to that we have some normal force here. Due to the force in the belt, we have some normal force, and due to this normal force we have a frictional force. We assume that force in one side of the belt and force in the other side of belt are different. Also, in this smaller region there is some mass of the belt, and due to this mass of the belt, we can have a smaller force, not a lot, but that force will be there, which is called a centrifugal force. And how to calculate this? And the magnitude of that centrifugal force is ds. So that is all for this small diagram. We say that the ds is centrifugal force, dn is normal force between belt and pulley, and fdn is frictional force, and the belt width is b and thickness of belt is t. That are all the variable. Also, we assume that the belt mass per unit length is m. So we know that the mass per unit length of belt is m. Multiplying m with length will give us mass in kg. And what is the length in this case? In this case, length is equal to this length. And this length can be calculated by simple equation s is equal to r theta, which we use a lot in physics as well. R is in this case this radius and theta is d theta. So this length is equal to r d theta. Total mass will be equal to total mass in kilogram will be equal to mass r d theta. So kilogram per meter multiplied by meter will give us mass in kilogram. So once we have mass, what is the magnitude of centrifugal force? Mr omega square. Mass is given, radius is given, omega will be the RPM of pulley. So substituting all values, mr omega square d theta, we have multiplied r with r, so mr square omega square, r omega, v is equal to r omega, velocity is equal to r omega. So we can convert this r omega in terms of v. Now fc in this term is equal to mv square or mr square omega square, and this is called centrifugal force. So centrifugal force in case of belt drive is mr square omega square or mv square. And what is m? M is mass per unit length of the belt. So once we have centrifugal force, then we will use static equilibrium condition, and in case of Cartesian coordinate we use equilibrium condition summation fx equal to 0 and summation fy equal to 0. But in this case we can, because our axes are not x and y, our axes can be radial and tangential, so we can use radial forces and tangential forces. So in case of radial forces, what are the forces in radial direction? This r direction, we have ds, also we have dn. This force, this angle will be equal to d theta by 2, because this is theta and half angle is d theta, and similarly this angle also will be equal to d theta by 2. So this force is downward and this will be the sine theta, so minus f sine d theta by 2 minus on this side f plus df sine d theta by 2. For very small angles we can say that, and all of these forces are equal to 0. For very small angle we can say that sine theta equal to theta, so sine can be neglected. So if we remove sine, the only term that left with ds plus dn minus f d theta by 2 minus f d theta by 2 minus df d theta. And here df is small and multiple of df multiplied with d theta will be further small, so we can neglect this term and we say that final equation is equal to dn will be equal to keeping f d theta by 2 plus f d theta by both minus and moving towards right, so d theta by 2 plus d theta by 2 f d theta minus ds, keeping it toward right, so the final equation will be this one. Similarly we can also do this for tangential forces, and what are the tangential forces? fdn is positive. Similarly f cos d theta by 2, and for small angle we can say that cos d theta is approximately equal to 1 for very small angle, and similarly sine d theta is approximately equal to d theta. So in this case f d theta by 2 will give us 1, and so for this will be the final equation. F plus d, this is minus, and this is the in the other direction, so it has opposite sign. So minus f plus f cancels out, so the final equation will be equal to df is equal to f dn. So in other words, in this small portion, change in force between left side and right side is equal to frictional force in the belt. Substituting the values, we have dn. Also, dn is equal to f d theta minus ds, and ds is equal to this term. So adding all the terms, we get a final equation, which is this one. And in this equation, simplifying this equation, we get this final equation. What is this equation? This is called non-homogeneous first order linear differential equation. And once we have this equation shows the behavior of system. But physically, to see the behavior of system, we have to have some solution of this equation. And the solution of this equation is not direct. And what we do in mathematics, non-homogeneous first order differential equations have a standard solution. What we do for not this type of equation, as we have standard, let's say you get exactly same equation in, let's say, in machine design for belts. Let's say in any other calculation in fluid mechanics, you get same equation. In thermodynamics, you get the same equation. In different fields, you get exactly same equation. Mathematics provide you the solution of that equation in terms of, because mathematics sees f, m, r, omega as variables, as system variables. So depending on your system, the solution will be different, but mathematics only provides you an idea of solution. So for this system, idea of solution is this. This type of solution has this type of equation has a solution like this: a e power f theta plus mr square omega square. Now this is a standard solution. How to apply this solution for our problem? In engineering, we use, in engineering and any other field, we use boundary condition. What is boundary condition? Simply speaking, let's say we have an equation y is equal to function of x plus some constant. We have this equation. How we apply this? This is equation 1. We can apply this equation. Y is the output. If you know value of x, let's say x is known and c is known, we can substitute. C is usually fixed, so we substitute value of x and we get value of y. So that is for any value of x. For any value of x, we have value of y. So that is standard mathematical solution. But for how to calculate c, because in this equation c is constant, we can say that we have this equation but we don't know c. Let's say for any point, for any input x, what is the value of y, and also that this equation satisfied your system. So what you do, you put the value of x in this equation, value of y in this equation, and you calculate c. Once you know c, you get the value y is equal to f of x plus c, which is known now. Now from that point, for every value of x, you can calculate value of y. So unknowns can be calculated from boundary condition. And what is boundary condition? The condition for which input and outputs are known for your specific system. Same theory is applied here. For this solution, do we have any point where we know input and output? And what are input output? Mass per unit length of belt will be known, radius of pulley will be known, omega will be known, theta will be constant, and coefficient of friction will be constant. So not theta, coefficient of friction will be constant. So only variable is theta. By changing theta, we can change f. So input is theta and output is f. Is there any point where we know theta and with reference to theta we know f? Yes, there is a point. Which point? We know that when the belt comes in contact with the pulley, there is a force on the belt which is equal to F2. And at that time, we know that theta equals 0. So because belt has just contacted the pulley, they just came in contact with the pulley, so angle of contact for that point on the belt is 0. Substituting theta 0, theta 0 will cause e power 0, which will give us 1. A F is equal to a plus mr square omega square, or a is equal to f minus mr square omega square. So the value of a is calculated from boundary condition. Now we substitute this value in the above equation to get this final equation. This final equation does not have a constant a, but a known, the constant a has been converted into the known system parameter, which is equal to f2 mr square omega square. Now for the system, f2 will be fixed, m, r, omega all will be known. So for any value of theta, we can calculate f. Applying another boundary condition, because for the belt motion, we don't need the forces at each and every contacting point of the belt. We don't need to have equation for all the points. We want to have force at here and force at this point. And what is the second point? The second point is when theta is equal to phi. So we say that when the belt leave the pulley, that point is contact point is theta can be represented by phi. For theta equal to phi, we have a force equal to f1. So substituting this value, we get another equation, and that equation, this 17.5 shows us the force at any point of contact of the belt, but this 17.6 shows the force at the point leaving the pulley. So this is the force. F2 is equal to a plus mr square omega square is the force at the point which just comes in contact with the pulley, and 17.6 is the force on the point of the belt which is leaving the pulley. So F1 and F2 are calculated. That was our main purpose. Simplifying this equation will give us a value e raised to power f phi f1 minus mr square omega square. And what is r square omega square? It is equal to centrifugal force. So e raised to power f phi equal to f1 minus centrifugal force divided by f2 minus centrifugal force. So for any system, f1, f2, fc, if they are known, phi is known, we can calculate what is the amount of f required for the system. For example, let's say for your system, you know what is the centrifugal force, mr square omega square. It is for the fixed data, it can be calculated. Let's say you know what is the angle of contact phi. If you know the phi, for that phi we can calculate f1. For that phi we can calculate, for phi equal to 0 we can calculate f2. We have f1, fc, f2, fc, phi. Only unknown is f. If we calculate f, we calculate f. This shows that our system needs a coefficient of friction equal to this f or more than this f. So you have to use a belt which has larger f than this value. For that f, the belt will not be slipped. Let's say after calculating, the value of f comes out to be 0.4, and your belt is, you are using a belt which is having a frictional coefficient of 0.3. It means that your required coefficient of friction is 0.4, but you are using a belt with a coefficient of friction of 0.3, so the belt will be slipping. So you have to use a belt with coefficient of friction more than 0.4. So you can use a belt of 0.5 or 0.6 coefficient of friction. So that is the purpose of this equation. This equation is also called belting equation. It shows how the forces change with the change in phi. Or you can just change the force f1 minus f2. If you calculate the difference, the final equation can be somewhat like this. Coming towards the second portion of mathematical calculation, in first portion we had calculated for f1 and f2 on start of contact with the pulley and end of contact with the pulley as a function of phi. And what is phi? Phi is the total angle of contact of belt with the pulley. In the second portion, we need another method to calculate the remaining variables will be encountered within the mathematical calculation. And what are the remaining variables? It can be initial tension in the belt. It can be torque transmitted by the pulley. Until now, uh, we have not seen transmitted torque by the pulley. In this second part, let's say you have a belting system. You have two belts, two pulleys. One this, second pulley is this. You attach these pulleys with a belt, and before rotating the pulley, you move this pulley, this right pulley, towards right to induce an initial tension Fi within this pulley. So we know that there is an initial tension within pulleys of both sides. That is already there. Now we also know that when this will be rotating, there will be some centrifugal force acting outward due to rotation of pulley. Uh, let's move it like this. Due to this rotation, there will be some centrifugal force acting in this direction. So we add a centrifugal component in both the equation. Now, if this pulley is moving, this pulley will pull the belt in this direction. So reaction on this belt will be more by amount T by D, because we have a torque of pulley. F is equal to T by D. This F is equal to T by D. So, and here same amount of torque, the pulley is pushing the belt on this direction. So the final force at this side will be equal to T by D. So there will be plus T by D, and we will be having minus T by D. So these will be the forces on upper and lower side of the pulley, or this will be F1 will be more, the larger force will be F1 and smaller force will be F2. Centrifugal force in terms of belt speed, we know that uh, V is equal to R omega. That equation is known. And what is omega? Uh, we can just calculate omega 2 pi R. So that's equation from V is equal to R omega. We can calculate V is equal to omega is equal to 2 pi F R into 2 pi F, and this 2 into R will give us D. So pi D N, where D is N is in radian per revolution per second. So velocity will be converted in meter per second. Also, we can use, if you say that the weight density is gamma, and what is the unit of weight density is Newton per cubic meter. Multiply it with area, cross section area, which is width of the belt and thickness of the belt. Multiplying with this, it will give us weight of belt per unit length. Now we just need to multiply with length to get overall weight of the belt. So we also know that F is equal to mr square omega square. And what is m? In this case, W by G is m. So, and R omega is V square. R square omega square is V square. So it is W by G. The final equation of centrifugal force can be written in terms of weight of belt as W V square by G, and W is equal to weight per unit length of the pulley. So that can also be calculated. So the final equation, which was this, we have already written final F force F1 and F2, that I have already explained. What we will do, we will add these two equations and subtract these two equations. By subtracting these two equations, we get 2T by D. And what is T? T is the torque transmitted by the pulley system. So the difference of forces multiplied, so this equation can be written as F1 minus F2 into R equal to torque transmitted. D by 2 is R. And the second term is, from this second term we can calculate initial tension in the pulley. So this is the required initial tension in the pulley. And now what we do, in this equation we have 2T by D, here we have Fi, just divide Fi divided by T by D. These two equations, divide one equation 1. Let's say this is equation 2 and this is equation 1. So 2 divided by 1 will give us this equation. And from this equation, we have value of f1 minus f2. The values are given. So using those values in this equation and simplifying, the final equation will comes out to be, that is using the first half of the mathematical equation and adding it with the second half, the final equation will be this. This shows that the initial tension in the pulley and the torque transmitted has a relationship. And what is that relationship? Let's say you have a pulley system. For that pulley system, phi will be fixed. Coefficient of friction, let's say for your system you have calculated a coefficient of friction and you have used a pulley with a higher coefficient of friction as well. Diameter, you have used a proper diameter pulley. So now torque transmitted by the pulley depends on coefficient initial tension in the pulley. If initial tension is 0, transmitted torque will also be equal to 0. So in order to achieve transmitted torque, we have to have a proper amount of initial tension. So the final conclusion is, the if Fi equal to 0, transmitted torque will also be equal to 0. So in order to achieve a proper torque or power from the pulley, we have to have initial tension must be provided. Once provided, it must be sustained and by a proper amount and maintained by the routine inspection. That's why for any belt you have to check either the tension is proper within the pulley. Otherwise, if there is some slippage, you have to tighten the pulley from any means, by any means. That's why in some of the system use idlers, and by pushing the idlers up outward or inward, we can increase or decrease the pre-tension in the pulley. We have this equation. From this equation, substituting in the previous equation the value of f1 and f2 that we already had calculated, like this f1 and f2, in these equations, substituting the values, we get a final value of f1 and f2 as a function of centrifugal force and fi, and phi will be known. So what does these two equations show us? These equations shows us how the forces are developed within the pulley system, and that is shown within a graph. Here you see that even if we don't have any initial tension, F1 and F2 will be equal to centrifugal force. So in horizontal axis we have Fi, initial tension, and the vertical axis we have F1 and F2. Even when Fi is 0, F1 and F2 both are equal to Fc, if there is Fc. Now we are increasing initial tension in the pulley, in the belt. Due to increase in initial tension, let's say we increase initial tension up to this point. At this point in the belt, we will be having F1 equal to this and F2 will be equal to this. So by increasing another some amount, this will be the F2 and this will be F1 in the pulley. Again further increasing up to this point, this will F2 and this will be F1 in the pulley. So what does it show? The change, the F1 and F2 difference is increasing. And what does it show? Difference in F1 and F2 multiplied by R gives us transmitted power. So this gives us transmitted power. More the difference between these two forces, more power will be transmitted. So we can say that if we take it to infinity, the power transmitted will be more. No, we cannot do this. Why? Because there is an upper limit of initial tension. This is the upper limit. How we calculate this? All the manufacturers provide us with the maximum tension that we can apply on a pulley. From that maximum tension, because F1 is more, so from that maximum tension, we can calculate Fi, and that will be the maximum initial tension that we can apply on a pulley, on a belt. So that will be the limit. Also, transmitted power is equal to F1 minus F2, change in force multiplied by V. Like I told you, F1 minus F2 into R gave us torque transmitted. Also, we know that torque is equal to P by omega. P is equal to T omega. Torque is equal to P by omega. In this case, we write H instead of P. So H by omega. So multiply omega here. F1 minus F2 multiply by R omega gives us V equal to horsepower. So final, not horsepower, power transmitted will be equal to difference of forces multiplied by V. Every manufacturer provide with the maximum amount of tension that can be applied on the belt. Also, there are some correction factors. One correction factor is CV. For belts, for leather belts, for any other belts, polyamide and urethane belt, CV equal to 1, and for leather belt, depending on the velocity, this value of velocity is almost 3 meter per second, and up to 3 meter per second, CV equal to 1, but after that you can check the value, the values are changing, decreasing. So the value of CV can be calculated from figure 17.9. Also, we have a table for value of CV. For example, if you are given that a pulley size is, this is a pulley size, and polyamide A2 belt is used, so you can use a value of CP equal to 0.96. So the final equation is, this is the initial tension, maximum tension that is provided by the manufacturer, FA. CP and CV you can calculate from this chart and the previous figure. B is the width of pulley that you are using, so you can calculate F1A. The value of this FA will be in Newton per meter. Manufacturer provide maximum tension that can be applied on a pulley per unit width of the belt, not on the pulley, on the belt. Maximum tension on the belt is in terms of Newton per meter of width of the belt. So multiply it with the actual belt, you will get value of F1A. So that value of F1A is being used here, and from that F1A we calculate Fi, and that will be FIA, maximum initial tension in the belt. Also, we have a service factor. For service factor, you have table 17-15, how to calculate service factor. This is a small table. You can just check what is the value of service factor. And is design factor, say KS there. Nominal, for example, you are required to transmit a power of 10 kilowatt. So the design value will be equal to 10 kilowatt. Let's say this is 1.2 and this value is 1.4. So the final value will be equal to 1.2 into 1.4 multiplied by 10. So it will be equal to more than 10. Let me calculate the value. 1.2 multiplied by 1.4, 16.8. So final value, design value will be equal to 16.8. So a pulley should be able to transmit a power of 16.8 kilonewton because your output power is 10 kilowatt. So design power has to be 16 kilowatt, so the system is able to provide a power of 10 kilowatt. So that's how we calculate power. So summarizing all the above, for any mathematical calculation, we calculate F and phi. What F is coefficient of friction, phi is angle of contact. From geometry of belt, we calculate centrifugal force. From centrifugal force, we calculate H nominal. That is, if we calculate, let's say HD, and HD divided by 2 pi n gives us torque transmitted, power transmitted, and then torque transmitted. We can calculate. Then from that torque, we have that F1 minus F2 equal to 2T by D. And why you are using F1A? Because we don't know both the value F1 and F2, and we say that F1, we are applying F1 equal to extreme value. So F1 minus F2 is equal to 2T by D. Once we know that F1A can be calculated from the previous equation, which we have just shown you, this equation, if we calculate F1A, substituting this value and F1A will be known, to D is also T is also known, so we can calculate F2. F2 and F1 is calculated, then we can calculate Fi. Once we are calculated all the values, we can substitute in this equation to calculate coefficient of friction of our system. If this coefficient of friction is the required coefficient of friction for your system belt pulley system. If you want no slippage, you have to use a belt which has a coefficient of friction higher than this value. If this coefficient of friction has higher value, then there is no slippage. If actual coefficient of friction is less than this required value, then there will be slippage. And after that, you can calculate factor of safety. All input and output values depend on the system. This is a one way of thinking. It might be possible that they ask you to calculate transmitted power. It might be possible that they ask you to calculate phi. It might be possible that they ask you to calculate belt dimension. They select a belt, select a diameter of pulley. So anything is possible, but overall this is a basic criteria to use the equations. So at the end, we have table 17.2 for different type of belt material, flat belt, and for example, if we are using A2 belt, for that belt the standard thickness is 11.11 inches, but in your book it is these data is given in terms of millimeter. Also diameter of pulley, minimum diameter of pulley is 2.4 inch. Minimum allowable tension is F1A in Newton per meter, or pound force per inch. Also, you have a specific weight. W is also given. It is gamma. And coefficient of friction also given. In your book, all these tables are in SI units. Also, for velocity less than more than 3 meter per second, you can use this table. For service factors, table 17.5 is like this. For example, if you are given that it is light shock situation, so you can use value between 1.1 and 1.4. You can either use 1.1, 1.2, 1.15, either value you can use, but just refer to this table. Minimum pulley diameters are given. Also, this table also shows minimum pulley diameter, but it's difficult to use. Just don't think of it. Pulley correction factor, CP. Let's say that pulley diameter is 10 inches, so it lies in this range. 10-inch pulley diameter for A3 type of leather belt, we have a value of CP equal to 0.87. Smaller pulley diameter, so it can be calculated. Also, there is size of crown is also given in a table. You can see these values. Just remember, both pulleys should be crowned in case of flat belt, especially when they are not horizontal. They has to be crowned. If this is not the case and you want one pulley uncrowned, then the larger pulley has to be crowned. The smaller pulley, if possible, you have to keep it crowned pulley, but if you want it uncrowned, it has to be smaller pulley. So that was all for theory section. In the second part, I will be explaining with examples how to select a pulley and how select a belt and how to solve problems related to flat belt system.